So last time we proved the following theorem. So we define this product, probability space. And we consider some function on there. And we say that such a function, such a random variable, is f certifiable if whenever we have a point in this probability space which have this high h value, then we can actually specify some not too many coordinates so that all points which has the same values on those coordinates, coordinates on I, they all have the h value at least s. If such thing exists, then we say this is f certifiable. And we say that this is k-Lipschitz if we change one coordinate. This x is actually x1 to xn. Each of them are like in this probability space, omega 1 to omega n. If we change one coordinate, then h value change almost k. Then we say this is k-Lipschitz. In this setup, if we choose a point in omega L random with respect to this product measure, it gave us the probability space on here using the product measure, then we have this inequality. So for any p and t, the probability that x is smaller than this and x is bigger than this are small. And how we are planning to use is that we will choose b so that one of those two are close to some constant. If b is a median, then we know that this is roughly half, or actually bigger than or equal to half. Then you just multiply, you just divide this to here, then you get you can show that this is actually small. So now we will consider some examples of application. So what we can consider, let's consider following. So let's say x is a point x1, x2 to xn, where each xi is a number between 0 and 1, chosen uniformly at random. And what you want to chosen independently uniformly at random. Let's just write it as a theorem. And what we will do is let x be the h of x, where this is the length of the longest increasing subsequence of this x. So we can consider that this is a sequence with this order. Then we want to show that we want to figure out, what's this value. So whether this value is very concentrated around some number. So with high probability, can we actually show that this is close to some number? And what we can conclude is that in this setup, we can actually find m, which will be our median, of course, later, which is roughly square root of m, such that for any t, we have the probability that x is much deviated from m is actually exponentially small. So this is what we want to prove. So most, natural way to attack this problem is use the azimuth inequality. So you can easily see that you can expose one by one. So you can consider two martingale, h of x. So let's just write the capital X, where x1 to xi are revealed. Then you consider this exposure martingale. Then you can easily check that once you change 1, then this expectation change by at most 1. So you can actually check that this H is a Lipschitz. So you can apply the azimuth inequality, then you can actually get the concentration. But in that case, here you can actually get something bigger, something like n to the 1 over 2. And here you get the expectation instead. But if you compute it, this expectation itself is again more or less n to the half. It's a theta of n to the half. So if you get the concentration of window size n to the half, then this is not particularly strong concentration and we are not so happy. So how we want to do it is we want to apply Taylor-Lagrange inequality to show a stronger concentration. And it's natural that it's obvious that we want to take this M as a median, but we also have to check that this median is as we want. And generally median is difficult to compute. Difficult to compute exactly, but lots of cases median and expectation, the mean, are not too far away. So lots of times what you can do is so in here you find some mean and say median. What you do is you first prove a concentration around mean. So meaning that probability that, so if we are concentrated around mean, around the expectation, let's write this, then the probability that the probability measure is concentrated here. So this part is small, this part is small, so this part has a probability more than 1 minus 0 of 1. As this is bigger than half, if you compute the median, then it has to lie inside of this window. So that's roughly one can measure this M. One obvious way is that you use the, as I mentioned, azimuth inequality. Then x minus this median is say 10 times n to the 1/2 is actually, we can show that this is smaller than 0.1. Then you can actually see that this writing is not good. Then you can actually see that M actually lies in between here because 90% of the measure right here, and then the median is at the point where we have half below, half above. So M is between that. That's one obvious way. But in this specific case, we can even take a simpler way. We don't have to really use the azimuth inequality. Let's say that M is median of x. Then we want to show that this is theta of n to the half. So if you have this x1, xn for let's say given set I, index set, which has size k. We can actually compute the probability that this number corresponding to I from the increasing subsequence. We know that this is 1 over k factorial. Let's say, let's consider this simpler form, which is slightly larger. So this is because first, the probability that two of them has exactly same value is 0, because we are choosing these numbers uniformly at random. So specific point, the probability of getting specific point is 0. So in that case, we can just consider this as and we are only considering which one is bigger and which one is smaller. So we just, take this and then we list, the smallest one and biggest one. So we list them in order. Then we get this permutation, and each permutation is obtained with the same probability because of each of xi is taking uniform measure. So out of k factorial choices, this is exactly the case that our permutation is 1, 2, 3, 4, 5, 6 to n, the identity permutation. So it's not difficult to show that, check that this holds. And how many choices of I there? There are n choose k, which is at most this number, choices of I. So if you let k with large constant times n to the 1/2, then the probability that h of x is smaller than k, meaning that there are no increasing subsequence of size k, is at least 1 minus 1 over k factorial times n choose k. Because if you take the union bound, this is actually bigger than the probability that there is at least one increasing sequence of length k. So you subtract that, and this is a probability. This is the lower bound of the probability that there are no increasing subsequence. And using these two, we can actually lower bound this. As if C is large enough, this is at least 1 minus 3 log 1. So with high probability, we have this. So this little o actually tends to 0 as C gets larger. Yeah, it doesn't matter. So as k is no, so what as long as this C is just some large number, then this go to 0 as n goes to infinity, because k and n are both big. So we have this. Then what does this mean? we have this c times n to the half, and we know that the probability that it is lying below here is 1 minus 0, 1. That means median is below here. And similarly, we want to also we can prove that with probability 1 minus 0, 1, it does not contain any decreasing sequence of length at least c times n to the, give me a moment, n to the half. Let me see. So if this holds, it doesn't contain any decreasing sequence of at least length that, then we know that the Erdős-Szekeres theorem, which is what we have learned in, where did we learn it? In the undergraduate graph theory, I think we have learned this. It states that if n is at least r minus 1 times s minus 1 plus 1, then in the above setup with for whatever sequence we have, which are sequence of distinct integers, no two of them are same, sequence of distinct real numbers, then either there exists an increasing sequence of length r, excuse me, or there is a decreasing sequence of length s. So it does not contain a decreasing sequence of length, at least this. Then by the Erdős-Szekeres theorem, it contains an increasing sequence of length at least 1 over c times n to the 1 half. Give me a moment. Let me check something. So what we know is that if we assume that this event happened and this event happened, so both of the events happen with probability 1 minus 0, 1. So that means with probability at least 1 minus 0, 1, which is bigger than 1/4, bigger than say 0.99, we have that the h of x lies between these two. That means the median also lies between this. So m is theta of n to the half. So now we have this. Now we can actually apply Taylor-Lagrange inequality, as this x is f-certifiable with f of s being s. Because if you have x1 to xn with h of x equal s, That means there are increasing subsequence of length S, and you mark them, and that coordinate is your I. So as long as you don't change this and you change something outside, we always can ensure that this new Y still has H value at least S. So this is F certifiable with the identity, function F. And F is Lipschitz. Because changing one coordinate only changes the value by one. So by Taylor-Lagrange, so we can apply Taylor-Lagrange inequality. What we have is that if we, let M be our B in the Taylor-Lagrange inequality, we have this. And the probability that the X is bigger than or equal to the median is, at least half. So we get this. Similarly, we take B such that P minus T times B to the half is M. Then B becomes M plus 1 plus 0, 1 times T times M to the half. Then what we get is the probability that X is bigger than B is, by the Taylor-Lagrange inequality, we can actually get this number here, this number on here, but which is M. So again, this is 2 times e to the minus t squared over 4. So combining this and this, what we have is that the probability that the X is deviated from the median by n to the 1, 4, because here we have a, give me a moment. This M is theta of n to the half, so this is roughly n to the 1/4. Then we have to, let me check a bit, change a bit. Let's just say omega of t squared, because I made some mistake here, because you have to take this t so that we actually get this t. So this t and this t are different. So from this t, you have to change this to t prime so that you get the right number later. But anyway, so from here you get the desired inequality. So this is one application. Let's consider one more application in the Kling number. Before, in theorem 7.10 in the lecture note, we proved that if G is chosen from the distribution of the random graph, G and half, then Kling number and K is some roughly 2 plus 0, 1 times log 2n. Then probability that is smaller than that is, we show that some constant times n squared over ln to the 8n. So it's concentrated. So with high probability, it's at least k. So that's what we have shown in 7.10. But we can actually improve this using the Taylor-Lagrange inequality. So with the same setup, we can actually prove that, we can actually improve this exponents on the bottom. So again, y be the, as before, maximum number of edges disjoint cliques of size k. Then what we have shown is, so before, let me check what it was the 7.10. Yeah, in 7.10 we show the lower tail has a small probability, and then it's not difficult to actually show that the probability that this is much bigger than k, say k plus some constant is also very small. So that's what we have shown when near the theorem 7.10. So we already know that it is concentrated around its mean. So its mean is some number which is roughly this. And it's already, quite concentrated around the mean. So as I mentioned before, this immediately guarantees that the median is close to this. So median M also satisfies that this with k being log. And it's easy to see that where it is Lipschitz. If you change one edge, then the maximum number of edges between k click can change at most one. And also y is f certifiable with f of s being k choose 2 times s. Because if there are s k clicks, edge disjoint, then the number of edges inside here are k choose 2, k choose 2, k choose 2, k choose 2. And in random graph, each pair being edges or not is the coordinate that we are considering. So as long as we take a k choose 2 times s many coordinates, and then we keep them, then whatever changes we made outside, the resulting graph still has y value, at least s, because it still contains s disjoint k clicks, s edge disjoint k clicks. So by the Lagrange inequality, what we have is the probability that y is smaller than m minus t to the m to the half times k choose 2 half is smaller than e to the minus t squared over 4 times probability of y bigger than m to the negative 1, which is again at most 2. So we get this. And we set that t be some constant times square root of m over k. Then what happened? Then so that m and t times m to the square root of m to the half times k choose 2 k over 2 are same. So we can let t be some constant times square root of m over k to make sure that those are actually become same. And probability that the omega of g is smaller than k is actually the probability that y becomes 0, which means that there are no clicks of size k, which is again this, which is because of our choice. What do we have? M is so exponential of minus omega of, we know that m is roughly n squared k to the 4. We take the square root, so n squared n k squared, and then you put another k third. Give me a moment. T is that you take the square, n squared k4, and then you, because you squared, you put k squared 4, which is roughly n squared over log 6n. So you get a, inequality with a smaller function here. In next video, we learn about one more result on the concentration, and after that we will move to next chapter.